start the presentation pointing out a typical feature, a distinctive feature of a rotating superfluid, which is the irrotationality of the velocity flow. This typically characterizes most superfluids, certainly both superfluids like helium and cold gases. And I would like to address the question to what extent this feature is general. The irrotationality of the velocity flow follows from the existence of an order parameter, and it's related to behavior of the phase of the order parameter, and is at the basis, at the origin of important superfluid phenomena that also in the framework of cold atomic gases have been systematically investigated experimentally, like the occurrence of quantized vortices.
Sorry.
Excuse me. Yes?
Sorry. But in this rotation, it's not rotation.
Yeah. In fact, I was mainly focusing on the both superfluids.
You can make both superfluid also rotation in different sort of parameters. Or was it on proximity? For some proximity, the curve velocity will be zero, but for some it is not. So it's not general.
Okay, I think that what I am discussing is exactly in this direction to show that both superfluids can exhibit a rotational velocity field and diffused vorticity. And I will give this a specific example in the case of spin-orbit coupled Bose-Einstein condensates. And what I was saying that this irrotationality is at the basis of quantization of vortices in ultra-cold atomic gases that was realized and observed in the many experiments, in the quenching of the moment of inertia below the critical temperature, in the occurrence of persistent current in toroidal configurations. The main point that I would like to make in this presentation is that in the presence of spin-orbit coupling, the usual relationship between the current and the gradient of the phase is violated, and this yields a violation of irrotationality and the emergence, in some cases that I will discuss, about diffused vorticity. And this is the key point that I would like to present in this discussion. And the question addressed in this paper, in this talk, concerns the calculation of the superfluid density in uniform metal and the quenching of superfluid density caused by spin-orbit coupling. And as a consequence of this and related to this is the violation of irrotationality and the emergence of diffuse vorticity. And if I have time, I would like also to present some results about the expansion of spin-orbit coupled Bose-Einstein condensate from an isotropic trap, which exhibits anisotropy because of the suppression of superfluidity along the direction of the spin-orbit coupling. The spin-orbit coupling that I will consider here is the simplest realization that has been already achieved and investigated experimentally in a rather systematic way in the group of Jan Spillman, and is based on the use of two lasers, polarized lasers applied to a Bose-Einstein condensate with the proper nonlinear Zeeman field to eliminate one of the three hyperfine components. And these lasers give a coupling between two hyperfine states, which eventually result in this form for the single particle Hamiltonian. And it's important to discuss the ingredient of this spin-orbit Hamiltonian. Px here is the canonical momentum. K0 is the difference between the wave vectors of the two lasers. big omega is the Raman coupling, which is fixed by the laser intensity. Delta is an effective detuning that is the result of the Zeeman field and of the detuning of the two lasers. This single particle Hamiltonian has very interesting features. In particular, it's characterized by a two-band structure. And if the Raman coupling is smaller than essentially 4 times the recoil energy of the laser's momenta, the lowest band exhibits two degenerate minima, which can host Bose-Einstein condensation. And vice versa, if the Raman coupling is larger than the 4 times the recoil energy, the lowest band exhibits a single minimum in the momentum, in quasi-momentum space, and can host, of course, a condensate for this value of for 0 value of the quasi-momentum. The corresponding phases that you can build starting from in these two different conditions correspond to the plane wave phase when the Raman coupling is relatively small, and the single momentum phase where you occupy a single quasi-momentum state. And these two phases have been realized experimentally, and also the phase transition between the two phases has been explored. And this is non-trivial phase transition, which is dominated by single particle dispersion, and exhibits, for example, a non-trivial divergent behavior in the spin polarizability. Now, a major motivation for using this spin-orbit coupling Hamiltonian is to generate synthetic magnetic fields, effective Lorentz forces, and producing quantized vortices without the problem of rotating the gas with mechanical, let's say, tools. And this is achieved and was achieved in this famous experiment by including a position dependence in the detuning field, which gives rise to an effective Lorentz force and to the formation of quantized vortices. For example, here you have no delta prime is the y dependence of the detuning. If delta prime is 0, you don't see any vortex. If you increase the value of delta prime, you produce several vortices. And these are vortices which are produced in a way which is different from the previous techniques that was based on the rotation of the harmonic traps in the group of Dalibard and of Ketterle in the old times now already. An important point that is the starting point of my discussion is that the spin-orbit Hamiltonian is translational invariant. It commutes with the canonical momentum, but is not Galilean invariant. This Hamiltonian breaks Galilean invariance since the physical momentum, which is fixed by this combination of canonical momentum and spin term, does not commute with Hamiltonian itself because of the Raman term. And so this means that the physics discussed by this Hamiltonian, if you work in the lab frame where the system is moving, or you move you work in the frame moving with opposite velocity with respect to the system, these physics are different. For example, Landau criterion for the critical velocity are different, and so there are typical features which are caused by the breaking of Galilean invariance. In particular, spin-orbit coupling Hamiltonian yields this result for the current density, which is not fixed only by the gradient of the phase as happens in usual Bose gases, but is fixed also by the spin component, the spin term, the spin density of the gas. And I will show now that this term here can produce a rigid rotational field when you apply a position-dependent detuning to to the system. The first thing that we investigated in this paper in collaboration with Lev and Shizong Zhang in Hong Kong and his collaborators was the suppression of superfluidity when you have such spin-orbit coupling. And to this purpose, what one has to do, one has to calculate the normal density defined as the static response to a transverse current operator, in particular zero temperature, which is the simplest case that we want to address. We have this expression for the normal density, and this according to the prescription developed by Gordon Behm already many years ago. In the Galilean invariant superfluids, like helium and usual BEC and Fermi gases, the normal density vanishes at zero temperature, and the system is fully superfluid. In spin-orbit coupled gases, the physical momentum, P, which enters the definition of the current, does not coincide with the canonical momentum and can give rise to excitations, and so giving a finite contribution to the normal density. Of course, in order to calculate these matrix elements and energy, one should know more about the excitation spectrum of the system. And this problem was investigated in the past years, both theoretically and experimentally. And I would like to show what are the features of the excitation spectrum of the spin-orbit coupled Bose gases. The excitation spectrum exhibits two branches. Because of the Raman coupling, only one branch is gapless and corresponds to a Goldstone mode in the small q limit, in particular to the propagation of phonons, while the second branch is gapped because of the Raman coupling. The theoretical predictions for the dispersion of these two branches was carried out in these papers and was experimentally confirmed with black spectroscopy experiments in the Chinese team in Shanghai by showing. So when we calculate the matrix elements needed to estimate the value of the normal density, one can easily realize that phonons, being longitudinal excitations, cannot contribute to the transverse current response. While the gapped branch, which is caused by the Raman coupling, can contribute, and is actually this contribution which is crucial in characterizing the behavior of the normal density of our system. And in particular, I don't give the details of the calculation, which are, by the way, very simple, and I would like also only to show the results. In particular, if you are in the plane wave phase, which means the Raman coupling is smaller than this critical value, the normal density behaves in this way, while if you are in the single momentum phase, the behavior is given by this second formula. And what's interesting that at the transition between the two phases, one finds that rho n is equal to rho, and consequently, along the direction of the spin-orbit coupling, in this special point, the superfluidity has been completely killed, and the system has a full normal behavior, which is rather surprising at first insight, because this system keeps Bose-Einstein condensation. One can calculate the Bose-Einstein condensation, the quantum depletion to Bose-Einstein condensation, and the effects are extremely small in 3 dimensions. And so the effect of the quenching of the phonon the velocity at the transition influences quantum depletion, but in a minor way. And the quantum depletion, which is typically 0.4% in the usual Bose-Einstein condensates, become 0.8% in the presence of spin orbit. So we have the typical feature of a system which is practically 99% Bose-Einstein condensed, but it's not superfluid as concerned the motion along the direction of the laser field. A question which is of course important is whether we can measure the superfluid, the normal density and the superfluid density, of course, which is rho minus rho n. The answer is can be attacked by looking at arguments based on some rules. In particular, what one finds that differently from Galilean invariant systems, they have some rule which is given by the energy-weighted moment of the dynamic structure factor, and which is given by the model-independent value Q square over m, is not exhausted by the phonon branch. And in particular, one finds that the contribution of the phonon branch is fixed by the superfluid density. On the other hand, the phonon branch exhausts completely the compressibility sum rule. And the final result is that one derives this macroscopic relationship which holds at zero temperature between the superfluid density, the velocity of sound, and the compressibility. Now, a peculiarity of spin-orbit coupling is that in first approximation, spin-orbit coupling does not modify the equation of states. So the equilibrium properties of the system, equation of state, pressure, compressibility, and the density profile in the presence of harmonic trapping are not modified by spin-orbit coupling, which instead plays a crucial role in modifying the dynamic properties and the transport properties, like the velocity of sound. The result is that one can employ this relationship together with the experimental value of the sound velocity, which are available now via Bragg spectroscopy experiment, to determine the experimental results for the superfluid density and compare it with the theoretical prediction. And the results are given here, and they show effectively that the phase transition between the plane wave and the single momentum phase, the superfluid density is dramatically quenched and suppressed with respect to the total density of the system. Of course, near the transition point, there can be problem fluctuations. For example, the validity of the mean field approach can be questioned. But even if one goes relatively far from the phase transition, one finds sizable effects which can be checked and in a more reliable and quantitative way, comparing theory with experiment. The second point that I would like to discuss now is what are the consequences of the reduced superfluidity on the rotational property of the spin-orbit gas. In particular, I present the derivation and the results for the moment of inertia of a gas trapped in an harmonic potential. And the moment of inertia is defined as the linear response to a static angular momentum constraint. And in the usual Bose-Einstein condensates without spin-orbit coupling, the rotational constraints induce a rotational velocity flow, which provides at the end the so-called irrotational value for the moment of inertia, which is related to the rigid value through the deformation, for the square of the deformation of the atomic cloud. So for isotropic, perfectly isotropic trapping in the xy plane, the deformation is vanishing and the moment of inertia is zero. So the superfluid is not able to rotate, and this was an important point in the understanding of the behavior, experimental value of the moment of inertia, and also is the basic starting point to understand that the only way to carry angular momentum for such systems is through the production of quantized vortices. Now, a useful way to attack the problem, to study the problem, to give an answer to these questions, is to develop a hydrodynamic formalism applied to a Spinor hydrodynamics, a Spinor configuration. And the main point is that when we consider equilibrium situation, or a small angular velocity, and in general, low energy excitations of the system, the relative phase between the two components of the order parameter is locked because of the gap caused by the Raman coupling. This relative phase can be important when one studies transition, like a Rabi-like transition between the two spin states. But if one wants to investigate the propagation of elementary excitations at low excitation frequency, when I say low, I mean frequency smaller, much smaller than the Raman coupling, then one can set the phi1 equal to phi2, and one can develop a theory where the quantities entering the equations are the total density, the spin density, and the total phase of the system. The equation of hydrodynamics take this form. And an important point to mention is that the equation of continuity is affected by spin-orbit coupling, and this gives rise to a new definition of the current, as I already pointed out in the previous slides, for the spin contribution of caused by the spin-orbit coupling. As I said, the equation for the phase is not affected by spin-orbit coupling, and at equilibrium, the density profile is not modified by spin-orbit coupling. The third equation is the new interesting equation that emerges from the formalism or hydrodynamic formalism that I have developed, which gives an additional relation between the gradient of the phase and the spin-orbit coupling. And this relation holds also out of equilibrium, and provided again we are studying a low frequency dynamics. In the presence of spin-orbit coupling, the angular momentum takes the additional spin contribution, which comes from the fact that the momentum along x is modified with respect to canonical momentum. And if we add the minus omega Lz term into the Hamiltonian, the relevant hydrodynamic equations take this form and can be solved analytically in the case of harmonic trapping if one works in the Thomas-Fermi approximation, where one neglects quantum pressure effects, which are expected to be small corrections in large systems. And I would like to show the behavior of the velocity field which emerges from the solutions. As I said, the velocity field is given by the sum of these two terms. The velocity field along x is the sum of the irrotational contribution, the x of phi, minus the spin contribution. And one can show, if one puts here the solution of the previous equation, that the spin contribution changes exactly the sign of the rotational term and provides at the end a value for Vx which is minus alpha y, while the velocity along the y direction is given entirely by the irrotational term and is given by alpha x. The conclusion of this simple calculation is that the velocity field takes a rigid body form, and in particular at the transition point, the moment of inertia, as I will show on the next slide, will take the rigid value, the rigid classical value. And these are the typical velocity fields which emerge. If one includes only the irrotational term, one would find such velocity field. If one includes the spin contribution, one finds this expression for the velocity field. And the moment of inertia that can be calculated once one knows the velocity field, again takes the rigid value at the transition, while it's smaller than the rigid value but still significantly different from zero when one is working either in the single momentum phase here for larger value of omega or in the plane wave phase. And a crucial point that emerges from this analysis is that since the rigid rotation is caused by the presence of the spin contribution, because the rotational term does not contribute finally to the angular momentum, the simplest strategy to generate the rotation of the gas is not given by the full rotation of the sample, which would imply the rotation of the lasers which generate the spin-orbit coupling and the trap. But it's enough to include in the Hamiltonian just the position-dependent detuning, which provides the crucial contribution to the rotation of the gas at a small angular velocity. So this provides a rotational framework without rotating the system, and this is the idea that, of course, was used by Spielmann and collaborators to produce vortices, including this term in the Hamiltonian, and for large values of beta, one expects to find vortices. So for small value of beta, we have given the solution in the previous slide, and the system does not produce vortices, but produces a rigid rotation of the gas. For larger value of beta, one produces vortices. And I would like to show here some some recent results that were derived in collaboration with our postdoc Chun Lai Ko, based on a Grosby-Tuyevsky simulation, where we have investigated what happens when you go from the rigid rotation at small value of detuning to the formation of vortices. And to this purpose, we have considered as a first case the point at the transition, the phase transition, but one can, of course, develop the calculation for all values of the Raman coupling. In this slide, so this is the Hamiltonian that we use. And the main point here that for small values of beta, vortices are not formed. And the systems rotate like a rigid body, confirming exactly the prediction of the hydrodynamic theory that I've developed in the previous slides. And you see these are the results for the Grosby-Tuyevsky solution. And what's interesting here is to look at the contribution to the angular momentum given by this canonical contribution and due to the spin contribution. Below the formation of vortices, which takes place with this choice of parameters at 6 Hertz, the canonical contribution gives no contribution to angular momentum because of the nature of the order parameter and the phase of the order parameter. While the contribution due to spin is the total angular momentum and follows the rigid body law. So the angular momentum is proportional, exactly proportional to beta, and provides the rigid value for the moment of inertia, which is essentially given by the ratio between angular momentum and the value of beta. When we go to higher angular velocity, we find a different scenario that was investigated, by the way, in this paper that was written by our chairman in collaboration with their collaborators. Victor and Jan wrote this paper in 2011, where investigating in a systematic way what is the most efficient way to produce vortices. And you see that when beta is larger, so larger than the critical value, you find a very interesting phenomena. The two spin clouds separate in a rather significant way. They move one with respect to the other in a significant way, and the spin contribution to angular momentum becomes very large. You have a jump of factor 3 with respect to the case just below the transition for the formation of vortices. And this to the fact because suddenly the two spin clouds separate. At the same time, the two spin clouds, the upper and lower part in the plane, acquire opposite phase modulation because of the spin density. I recall you that this relation follows from the equation of continuity, and so to the extent that you have a spin density in the system, automatically you need to have a position dependence in the phase to compensate to produce the final equilibrium properties for the gas. At the interface between the two components, so this is spin up, this is spin down, and this is the total density, which is not modified in a dramatic way with respect to equilibrium. Of course, it requires a deformation, but it's not so dramatic. But the dramatic change in the spin distribution, and at the interface between the two clouds, you have a deformation of an array of quantized vortices, which, by the way, have an opposite circulation with respect to the angular momentum given by the spin component. And so you find that the canonical contribution to angular momentum, which is associated with the presence of vortices, is negative and reduces significantly the total angular momentum of the system. Our plan now is to investigate more how one can also experimentally point out this feature. That would be very interesting to do. But this was not the strategy used by Spillman, because they used a different strategy in order to ensure the emergence of vortices within each spin component in order to observe in an easier way after expansion these vortices. 2 minutes. Okay, so let me finish and conclude by showing that the same idea can be applied if one considers spin-orbit coupling in the presence of a toroidal configuration. And in this case, it's possible to use Laguerre-Gauss laser beams to transfer angular momentum and generate a spin-orbit coupling in the toroidal trap. So in the absence of spin-orbit coupling, the quantum of circulation is quantized according to these fundamental units h over m. If one includes this spin-orbit coupling, one finds a simple result where one finds that an interesting new result where the quantum of circulation is modified, is suppressed by spin-orbit coupling. And in order to measure this effect, one should very likely avoid to use interference phenomena that are typically employed by the group of Jean Dalibard, for example, to point out the occurrence of quantized vortices. One should measure directly the angular momentum that you have circulates in the system, which is possible using a Doppler-like effect that we employed, by the way, in collaboration with Bill Phillips last year to measure the quantum of circulation without spin-orbit coupling. So this is another interesting direction. I have no time to discuss the anisotropic expansion from isotropic trap. If somebody wants to discuss, we can discuss later. And so I think we can go to the conclusion. The main conclusion is that the superfluid behavior of a BEC gas is strongly modified by the breaking of Galilean invariance. And of course, this superfluid is not destroyed completely, in the sense that, for example, if you rotate fast, you generate still vortices, which are typical consequence of superfluidity. But what's interesting that this is there are new features of superfluidity, which probably are related also to the physics of superfluid helium-3, as you said. There are phenomena of superfluidity which are, let's say, more exotic with respect to the standard features of irrotational superfluids. And what I emphasize that the quenching of the superfluid density can be extracted from the measurements on the velocity, that the moment of inertia is strongly affected by spin-orbit coupling, and also the quantization of circulation. Concerning the future projects, I anticipated already some results about what happens when we go from the rigid rotation to the formation of quantized vortices. Then a challenging question is how to test experimentally the fact that you have a rigid rotation. Because if you don't see the vortices, it's not easy to reveal the fact that the systems rotate in a rigid way. There are, however, possibilities to study the coupling between the rotation and the collective oscillations. And the most famous example of this coupling is given by the Foucault pendulum. In our frame, the Hamiltonian contains the minus omega Lz, where omega the rotation of the Earth, and the dipole frequencies have opposite value if they are clockwise or anti-clockwise, and the precession is a fundamental and historical feature proving the rotation of the Earth. In some sense, here we are able to probably, likely, and this is what we are studying, to do the same, probing the consequences of the spin detuning, the position dependent of the detuning on the precession of the center of mass oscillations. Last point that where I am presently involved is the study of superfluidity of the Rush Hamiltonian, which is of course attracting a great interest because of non-abelian nature of the vector potentials, where one expects and one finds also in that case interesting phenomena. Thank you very much.